Okay, so in order to get this session started today, I'm just going to draw a couple scenarios on the board, and all you need to do is try and create force diagrams for each of those three, and that's all. No force equations. You don't have to do any weird angles or rotating your axes. Just draw what forces are present for these conditions. So there are your three scenarios. Alright, so if we want to take a look at these force diagrams then, let's take a look first at the thing hanging from the ceiling. So we start with a little dot. What's one force that's present? Yeah, gravity's going straight down. And what's the other one? Tension, because we've got a string holding it up. Resist the urge to call this a normal force. Usually upward forces aren't like normal forces, but if you have something hanging from a string, we call that a tension force. And these two arrows should be the same size. So, how about this one? A block is at rest on a table. Once again, I'm guessing we have gravity. What's going up in this case? What's it? Normal force, yes. Now, how, if at all, would this force diagram change if this object was moving at a constant speed on a frictionless surface? So I suppose the main question would be, would it change? No, because if that object is already in motion and there's nothing opposing that motion, it will remain in motion unless some other force acts on it. You don't need any horizontal forces if your object is already moving. Realistically, though, of course, you'd have friction going to the left. But yeah. How about this thing? The block is on this little incline here. I'm going to draw this force. No, I'll do it separate. So I'll do the hard one. Here's gravity. You're welcome. So what other two forces are present? Normal force? Is normal force going straight up? No. Angle just a little to the right, yeah, because normal force always goes perpendicular to the surface. So normal force might be something like that. And is there anything else? Friction. Friction, yes, because there's no motion. Velocity is 0, So that means friction must be holding this in place. Very good. And because it's not moving at all, we'd call that static friction. So a force of static friction. This is the sort of thing to expect from page 1 of the test. Now the next page is a lot of multiple choice, and we'll see if you're okay with this here. Let's say somebody is pushing on a big table, maybe like this one right here, pushing with 100 newtons of force. How many newtons of force is the table putting back on that person? 100 newtons. But what if I push this table and it's moving at a constant velocity? Then how many newtons of force is it putting on me? You sure? Good. 100 newtons, exactly. Every time you're putting one force on the object, it's putting the exact same force back on you. But what if not only is this object moving, but it's accelerating? I'm pushing it with 100 newtons so hard that it's picking up speed, and it's busting through walls and everything. How much force is it putting back on me? Good guess. 100. It's the same. Regardless of what's happening with motion. You must have this drilled into your minds before this time tomorrow. Because Newton's third law is always true. If you put a certain force on an object, it's putting that same force back on you. Now again, the reason that sometimes you get things like acceleration, those two forces, although they're opposed, you might have different friction on either of those. You know, you could be putting 100 newtons of force on something that is just sliding across the floor. Meanwhile, you've got your shoes on that provide more friction. That's why you're able to get it to move that way and have those forces still be equal and opposite. But the main thing you have to remember is that Newton's third law is always, 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 always true. What would the action-reaction pair to this scenario be? As I push on the table. Yes?
Mr. Hathaway pushing on the table is equal to the table pushing on Mr. Hathaway.
Nailed it. Force of the table on Mr. Hathaway is equal to the force of Mr. Hathaway on the table. So make sure you're aware of those Newton's third law pairs. Okay. Let's say I've got this cute little cup. I really like this cup. It's got stars on it. I got it as a gift one year from some astronomy students. And if you put hot chocolate in it, it lights up and you can see constellations.
There's hot chocolate?
Well, anything that's hot. Yeah. I could, maybe I should fill it with water at the end of class and put it in the microwave and show you. It's pretty cool. So let's say I take this cup and I'm pushing it across the table. As I push with a constant force, what forces are present on that mug? Just kind of name them off for me. Gravity? Friction? Normal force? Applied force. Anything else? Not really. No. If we were considering my hand, then I'd have to do the Newton's third law pair thing. The force of my hand on the cup is equal to the force of the cup on my hand. But if it's not specifically asking for that, you don't have to worry about it. What about this? What are the forces present right after I'm done touching it? As it's moving this way, but my hand is no longer in contact. Then what forces are there? Normal, gravity, and friction, yeah. But it's still moving this way, so shouldn't there be some force from my hand left over on that cup? After all, it's moving to the right. See, a lot of people shake their heads, and that's good. So what's wrong with that reasoning? That's exactly how I'd start the sentence. Yeah, force is a push or a pull. If I'm not pushing or pulling that cup anymore, then my hand doesn't have any force left over onto it. Of course, Galileo would say that as you let it go, it retains that force, but Newton properly explained it when he said that once you let go, there's no leftover force. So it's moving in this direction because that's naturally the velocity that you gave it when you were touching it. But when you let it go, it's slowing down because there is an external force acting, and that is friction. Okay. What happens if I take the same cup and let's say I'm pulling it with a string. So I'm pulling it with a string, and after some time that string snaps. Which of these four ways best describe the motion of that cup immediately after the string snaps? Number one, it immediately slows down. Number two, it moves with a constant speed for a while, and then it slows down. Number three, it remains at a constant velocity forever. Or number four, it's going to continually speed up forever. Should I go through those again?
What about that? It was just slows down. Yeah. I mean, not after like a long time, but it'll take a
Okay.
It starts slowing down immediately because there's no more force out there.
Okay, so I'm hearing two different answers. Sounds like you're deciding between 1 and 2. Number 1 was an immediate slowdown, like Trey seems to be advocating. Or number 2, moves at a constant speed for a little while, and then it starts to slow down. You say what? Okay. So the thing that we have to consider when we're answering this question is just Newton's first law. An object in motion is naturally going to stay in motion until a separate force begins to act on it. As soon as that string snaps, is there a force going against its motion? Yeah. So because friction is immediately acting from that point in time, you are going to have an immediate slowdown from the moment that that string snaps. If you're looking at it, you might not be able to tell right away, but it is starting to slow down immediately. So you do want to make sure you're aware of that. Got Newton's apple right here. And I take Newton's apple, and I throw it. What forces are acting? Well, that was fun. What forces are acting on that apple as it is flying through the air? Gravity? Just gravity, absolutely.
What about the air resistance?
Yeah, if you have to take air resistance into account, it will specifically tell you. But yeah, if we're not taking air resistance into account, gravity is the only thing that's acting on that ball. As it's flying through that air, doing, its parabolic trajectory there, it's tempting to think that there must be a lot of different forces at work causing that motion to be so sophisticated, but there aren't. It's just gravity. That combined with the fact that you gave it a starting velocity is why it travels the way that it does. So yeah, no normal force, no leftover force from the hand. Okay, let's say in that example where I was on the skateboard and I pushed off the wall one time. Let's do a force diagram just for me as I'm on that skateboard and my hand is in contact with the wall and I'm pushing off so that I get some sort of velocity there. It's a big skateboard. So what's present as I am actively pushing off the wall, giving myself an acceleration? Gravity, for sure. A little bit of friction. We'll say I'm moving to the right, so friction would then be this way. Anything else?
Wait, so you're actively, your hands are on the wall.
My hands are on the wall, I'm actively pushing off of it. I heard normal force.
So then on the applied force?
Yep. Because I am actually pushing. A force is a push or a pull, so if I'm pushing off that table, I've got an applied force in this direction. And that would be how I would draw that.
So the applied force goes, like, the arrow goes facing the way that a person, facing the direction of the person who's pushing.
It goes facing the direction you're going to be moving because of that force.
Oh.
So, like, even though I see what you're saying, if I'm standing like this, pushing off the wall, it's like I'm pushing to the left. But my motion is to the right. So the applied force would be in that direction. Because it's essentially what we're representing here is how the table is pushing me as I exert a force onto it. So, how would this force diagram change if I'm no longer in contact with the wall and I'm freely moving across the floor, slowing down ever so slightly? Yeah. Applied force goes away. And so now we have this interesting scenario where I'm moving to the right, but the only force that's acting on me is one that's to the left. And again, the way we reconcile this is the fact that an object in motion naturally stays in motion unless something else is acting on it. And in that case, that's friction. So even though I'm moving to the right, I'm slowing down because of that extra force. How about this? What about when I encounter the wall on the other end? Maybe I want to draw a force diagram for, let's draw a force diagram for the wall, and let's draw a force diagram for me. So normal force and gravity are still there, friction is still there, and as I encounter the wall, it's going to provide a force on me to help me stop. So first off, what direction would that force be? Right or left?
Oh, I'm sorry. Can you say that again?
Sure. When I eventually run into the wall and it stops me from moving, it's providing a force on me, providing a push. What direction is that push? To the left or to the right? Left, yeah, exactly. Because if it was to the right, I'd be picking up more speed. So I would say, now that we're doing force diagrams for two objects, I would call this the force of the wall on Mr. Hathaway. And that would be going to the left. Meanwhile, you've got the wall here.
So would the friction switch sides too?
What?
If the wall,
Say that again?
if the wall is making you go back this way, would the friction switch sides?
Only if I start moving in that direction. But in this case, I'm slowing myself down. So friction's still going to the left. Now for this wall, we'll just treat it like something that's by itself. So this way we can just think of it easier in terms of the fact that it has some gravity.
Wow.
There's a normal force going up. And this is kind of interesting because there's going to be some friction on this wall because I'm going to hit it, I'm going to run into it, but it's not going to go anywhere. So what kind of friction would I call that? Static or regular? Static friction, yeah. So when I run into this wall, I am basically trying to push it this way. So that means the force of friction would be to the left. Now, as I'm encountering this wall, I am trying to essentially push it to the right. As I run into it, I'm exerting that force. So that force would be to the right. And what do you suppose I'd call that one? Yep, force of Hathaway on the wall. And once again, all Newton's third law is saying is that this force right here is going to be equal to that one right there, no matter what happens when I hit that wall. If I bust all the way through it like the Kool-Aid man, or if I run into it and I fall backwards, the force that I exert on that wall is the same force that it's putting right back on me. Questions on this? All right. The only other thing I want to emphasize before we dive into, basically those are the first 14 problems. And then the last one is a more difficult one. So before we jump into that, I just want to make sure you're aware. In terms of these force diagrams, if you think of the forces acting horizontally on this particular dot that represents an object, this would mean, because there's nothing horizontal, that its horizontal speed is not changing. If it's already moving, it will continue moving at that speed. If it's at rest, it will remain at rest. Its velocity is unchanging, whether it's holding still or moving. Same thing would be true if these forces are the same size. If these arrows are the same length, then this object's speed is not going to change. The only way its velocity changes is if one of these arrows is bigger than the other. So if I make this arrow larger, that would correspond to a scenario where this object is either going to be picking up speed to the right or slowing down to the left. So yeah, the main thing you got to know is that when you've got a bigger arrow, that means your velocity is changing. Okay. So, on to the hard stuff. We did one of those incline problems yesterday. Which of these two do you feel less comfortable with? The kind where we've got a force going into an object, or the kind where maybe it's being pulled at an angle?
Yeah, I don't remember either.
Okay. They're both kind of the same problem, it's just different force diagrams. Anybody feel strongly about these?
Maybe we'll go out.
Sure. We'll do this one then. We'll go through that one, and then we'll get through as far as we can with the other one before class ends. Yep. Okay, so we need a couple things here. First off, what's a fun mass to use?
From what?
What's a fun mass to use? What number?
72.
72 kilograms is the mass of this box. And what's a good angle to use?
I would say 50.
What's that?
50.
50 degrees, all right. And we'll just say it's pulled with a force of 100 newtons. So, if this is the case, we'll also say that the friction is great enough that this object isn't going anywhere. So for this kind of a problem, generally we'll be asked for two things then. What is the force of static friction? And what is the normal force? So, in order to solve this, we got to start with a force diagram. And if you see a problem like this on the test, you should be very excited because that means you don't have to do anything with your axes being rotated in some funky direction. So we can start with what we know. We know we've got gravity going straight down. We know we've got a normal force going up. Would that normal force in this case be larger or smaller than gravity?
Smaller.
Very good. Because we're pulling up, and that means the table has to do less work or effort to keep that box from falling through. And of course, we've got our tension force. Now, 50 degrees is a bit bigger than that. And because there is no motion on this box, we're going to have some friction going to the left. So we're looking for force of static friction, and we're looking for normal force. We want to get those somehow. And in order to do that, we have to look at things in the x and the y direction. I'm going to quick put this up as 100 because we know that. So what do you think? Should we do x or y direction first? X, okay. X is actually the easier one to do first because we've really just got two forces going in the x direction. We've got friction going to the left. Meanwhile, this delinquent tension force is partially acting horizontally to the right, and partially it's going up. So I'm going to call this the tension in the x direction. Here's our 50 degrees. So that's our force diagram there. So if I want to figure out what's going on with force of static friction, I just have to create a force equation in its direction. In this case, that's the horizontal direction. So horizontally, we've got tension going to the right in the x direction, minus force of static friction going to the left. And those will subtract to be 0. And just like last time, you can kind of see where this is headed. If I want to solve for my force of static friction, I'm just going to take this part of the equation and move it over to the right. And exactly. Force of static friction is going to be equal to the tension in the x direction. And so now this turns into a SOHCAHTOA problem. If I want to solve for tension in the x direction, I got to solve for the adjacent side of this 50-degree angle. And because it's the adjacent side, that means I got to use cosine. Cosine of an angle is equal to adjacent over hypotenuse. So the adjacent side is what we're looking for. Hypotenuse is given to us as 100. (100) times the cosine of 50 then is what you would use to get your final answer, because you're multiplying both sides by the 100. And if your calculator is in degree mode, which you should, I'll try and remember to remind you of that as you come in tomorrow, you should get 64.3. And because tension in the x direction is equal to force of static friction, we're done with that part. Questions on this one? Okay, the y direction, when we solve for normal force, is going to be a little bit more complicated because in the y direction, we've got more than just two forces here. So in the y direction, we've got normal force going up, we've got gravity going down, and this tension force is partially pulling upwards. So we have to take that into account. So we would call that partial upwards force then the tension in the y direction. And from here, we ought to start making our force equation. So again, all a force equation is all the forces going in one way minus all the forces going the other way. So everything going up is normal force and tension in the y direction. So we're going to add those. Going down, we've only got gravity, and that's all. So this is what our force equation looks like. You really should. Because in order to solve for normal force, we have to isolate it in that equation. So if I'm going to get my normal force by itself, which is our whole goal here, I got to move force of gravity over to the other side. That makes it positive. And then I'm going to move tension in the y direction over there too, and that'll make tension negative. So this is the equation you end up with then. So now it's just a game of calculating those two things and doing the subtraction. So force of gravity is the easier one, so let's just start with that. Force of gravity is just mass times 9.8. So 72 times 9.8 is 706. Tension in the y direction is going to be a little bit more complicated. Tension in the y direction is over here. It's the opposite side of our 50-degree angle. So if I want to solve for the opposite side, I got to use sine. An alternative would be to use tangent if you wanted to use the force in the x direction that we just calculated. I usually just stick to sine and cosine to be consistent, but whatever you feel like. So tension in the y direction, then I'm going to use a sine function to solve for. So sine is equal to the opposite side divided by the hypotenuse. So the opposite side is equal to FTY, and the hypotenuse is 100. So tension in the y direction, like the previous example, is going to be 100 times your trigonometric function. So I get 76.6 for that. So that's my tension in the y direction. And this is my force of gravity here. So all I got to do to get my final answer for the normal force is I got to take 706 and I got to subtract 76.6. And that will get me my final answer, which is about 629 or so. So that would be equal to your normal force. Questions on that? Okay. Well, let's get as far as we can on that third possibility there. So we might as well use the same mass here. 72 kilograms. Maybe now we're coming in at a 50-degree angle. We'll still say the velocity is 0, and we'd still be looking for the same two things, normal force and friction. So, if I want to approach this one, the only difference between this and the last one is really in the force diagram. Once you get your diagram, it's pretty much the same procedure. So, let's get that diagram going here.
What's the mass?
72. And we'll keep the force the same as well, 100 newtons of force. So gravity's going down. Normal force is going up. Is normal force bigger or smaller here? Bigger, absolutely, because we're pushing down on the object, and that means the ground has to exert more effort to keep it from falling through. So there's also going to be some friction here because it's holding still. And if we're pushing down like this, the object would want to move this way, which means friction has to be going this way. Finally, we've got this 100 Newton force here. And I'll just walk you through the slow way to figure out how that arrow works again. If we're looking at this, it would be like saying that we've got a 50 Newton force, or 100 Newton force, coming in like this at a 50-degree angle. But of course, our arrows cannot be going into the dot, they got to be coming out of it. So the way that you do this then is you would just follow that arrow all the way through. And by math, you would know that this angle is going to be the same as this angle. So here's 50 degrees. And here's your 100 newtons right there. And that's how you would properly draw that force diagram. Yeah, I would then erase this. If you can just draw it like this from the beginning, that's totally fine. Okay. So, if I want to figure out let's do x direction first again, force of static friction. There's two things that I need to consider. Number one, friction's going to the right. Number two, this applied force is sort of pushing to the left. So that applied force is coming in at this angle, so it's not acting exactly horizontally. Therefore, I gotta actually figure out how much of that force is going horizontally. Call this the applied force in the x direction. So, force equation is going to be applied force in the x direction minus force of static friction equals 0. And just like the last time, if I want to solve for force of static friction, I'd put it on the other side. And you see that those two things are going to be equal to each other. So now I just got to solve for the applied force in the x direction, which is another SOHCAHTOA bit. Applied force in the x direction is the adjacent side of this 50-degree angle. And if it's adjacent, your mind should immediately go to cosine, because the cosine of an angle is equal to the adjacent side over the hypotenuse. We're going to get the same answer as we did in the last one now.
64.3.
Yeah, I think that's right. Yep. So applied force in the x direction is 64.3. You multiply both sides by 100 to get this applied force in the x direction by itself. 64.3. So that's also equal to your force of static friction then. Now, let's say that this was moving at a constant velocity. If this was moving at a constant velocity, we would do the exact same thing. The only difference is it wouldn't be static friction, it would be regular friction. Because if you're moving at a constant velocity, these two forces are still going to be the same size, because it's not speeding up or slowing down. Looks like we'll have to end there. Vertically, you'd follow the same procedure as the last one. You will get a different answer, though, because now normal force is being opposed by those two, so you'd be adding the numbers instead of subtracting them. But it would be the same procedure.
You know what to add it to the box again?
Just from the equation. Like this equation, see if I can get it written down quick, would be normal force up minus everything that's going down. So that would be applied force in the y direction plus force of gravity. So you'd move these two things over here, and then they're added together.
So when there's an arrow going into the box, you should add.
Yes. Yeah, that's a good way to think of it.